Hello students, welcome to KSN Classes. Today we will discuss a few problems on differentiation. The first problem is, let fx be a real valued differentiable function not identically 0 such that f of x plus y to the power of 2n plus 1 is equal to f of x plus f of y whole to the power of 2n plus 1 for all n belongs to n, where n is a set of natural numbers and x comma y are real numbers and f dash 0 greater than or equal to 0, then find f of 5 and f dash 10. So this is a problem based on the functional equations. It is given that fx is a real valued differentiable function not identically 0. Now here we will discuss the solution. We will consider the equation given f of x plus y to the power of 2n plus 1 is equal to f of x plus f of y whole to the power of 2n plus 1. 2n plus 1. Let us call this equation as 1. Now put x is equal to y equal to 0 in this equation. It will become f of 0 equal to f of 0 plus f of 0 implies f of 0 is equal to 0. f of 0 equal to 0. Now here it is given that f dash 0 greater than or equal to 0. Now let us consider f dash 0. By definition, limit extends to 0, f of x minus f of 0 by x minus 0. Now here this is limit extends to 0, f of x by x, because f of 0 is 0, this is f of 0 is 0, so f of x by x. For x greater than 0, here x being positive and f dash 0 being greater than or equal to 0. So this is greater than or equal to 0. Now x being positive, this fx must also be positive, implies f of x greater than or equal to 0. This is one condition. Now by taking f of x plus y to the power of 2n plus 1, now in the first equation put x is equal to 0 and y equal to 1. In first equation we have f of 0 plus 1 to the power of 2n plus 1 is equal to f of 0 plus f of 1 to the power of 2n plus 1. Now here this is 0, 1 to the power of 2n plus 1 is 1, f of 1, and here f of 0 is already observed it 0, therefore this is f of 1 to the power of 2n plus 1. Therefore I can write f of 1 into 1 minus f of 1 to the power of 2n is equal to 0, implies f of 1 equal to 0 or f of 1 is equal to 1. So here there arises two cases for f of 1, it is either 0 or 1. Now case 1, let us consider the first case. Case 1, suppose f of 1 is equal to 0. Now in the equation 1, let us put y equal to 1. Put y equal to 1 in the first equation. So here we have f of x plus 1 to the power of 2n plus 1 is equal to f of x plus f of 1 to the power of 2n plus 1, f of 1 to the power of 2n plus 1. f of 1 is 0, therefore this is 0, implies f of x plus 1 is equal to f of x. And therefore now put x is equal to 1, f of 2 is equal to f of 1. So f of 1 is equal to f of 2 is equal to f of 3 is equal to so on. But f of 1 is considered to be 0. This value is equal to 0. Therefore, f of 1 equal to 0, f of 2 equal to 0, f of 3 equal to 0, and everything is equal to 0. But it is given that the function is not identically 0. It is a contradiction. It is a contradiction because or since f is not identically 0. Now case 2. In case 2, consider f of 1 is equal to 1. Now again put y equal to 1 in the first equation. We have put y equal to 1. Then f of x plus 1 is equal to f of 1 plus f of x plus f of 1 to the power of 2n plus 1. Here it is f of x plus 1 is equal to f of x plus f of 1 is 1. F of 1 is 1. So this is 1. Now put x is equal to 1 and all. We will get f of 2 is equal to f of 1 plus 1. F of 1 is 1. Therefore this is 2. Put x is equal to 2. So f of 3. F of 3 equal to f of 2 plus 1. This is equal to 3. So here f of 1 equal to 1, f of 2 equal to 2, f of 3 equal to 3. So likewise you can proceed, and therefore here proceeding we get f of x is equal to x. F of x is equal to x. Implies f of 5 is equal to 5. F of 5 equal to 5. Since f of x is equal to x, if you differentiate, f dash x is equal to 1. Implies f dash, in place of x, if you put 10, f dash 10 equal to 1. Therefore, f of 5 equal to 5, f dash 10 equal to 1. So 5 comma 1 is the answer. The second option is the answer. The second problem is match the following. So we have to match the problems given in the first column with the answers in the second column. We'll take the first problem. F dash x is equal to root of 3x square plus 6 and y is equal to f of x cube. Then at x is equal to 1, dy by dx is equal to. Let us start the solution. First one. Y is equal to f of x cube. On differentiating, dy by dx is equal to f dash x cube into 3x square. Now dy by dx at x is equal to 1. This is equal to f dash 1 into 3. Now from the problem it is given f dash x is equal to, given f dash x is equal to root of 3x square plus 6. Now f dash 1 is equal to 3 into 1 square, 3 plus 6, 9, 3. Therefore dy by dx is equal to f dash 1, 3, 3 into 3, 9. So this is the value of the first question, that is yes. Now the second question. If f is a differentiable function such that f of xy equal to f of x plus f of y for all x comma y belongs to R, then f of e plus f of 1 by e. Given f of x comma y is equal to f of x plus f of y. Now we are asked to find out f of e plus f of 1 by e. Put x is equal to e, y equal to 1 by e. Implies f of e plus f of 1 by e is equal to f of e into 1 by e, that is f of 1. Now again you call this as the first equation, you call this as the second equation. Put x is equal to y is equal to 1 in first equation. F of 1 is equal to f of 1 plus f of 1 implies f of 1 is equal to 0. Therefore, f of e plus f of 1 by e is equal to 0. That is R. So, the solution of the second problem is R. Now, we will look into the third one. Given f double dash x is equal to minus fx and f dash x is equal to gx. If you differentiate it, f double dash x is equal to g dash x implies g dash x is equal to f double dash x is equal to minus fx. So minus fx. Now hx is equal to f of x whole square plus g of x whole square. On differentiating, h dash x is equal to 2 into fx into f dash x plus 2 into gx into g dash x. This can be 2 into fx into f dash x is gx plus 2 into gx into g dash x is minus fx. Therefore, both are same with opposite signs. It is 0. Implies h dash x equal to 0 implies hx is a constant function. Say k, where k is a constant. Now, given that h of 5 equal to 9, that is equal to k, implies hx is equal to 9. h10 is equal to, put x is equal to 10, this is 9. So, the answer for the third one is again yes. Now, we will look into the fourth one. It is given that y is equal to tan inverse cot x plus cot inverse tan x. 5 by 2 less than x less than pi. We are asked to find out dy by dx. Differentiating with respect to x, dy by dx is equal to, it is in the form of tan inverse x. 1 by 1 plus x square, that is cot square x into derivative of cot x minus cosecant square x plus derivative of cot inverse tan x. It is in the form of cot inverse x minus 1 by 1 plus x square, that is 1 plus tan square x into derivative of tan square x secant square x. Here 1 plus cot square x is cosecant square x. So cosecant square x gets cancelled, minus 1. Secant square x, 1 plus tan square x is secant square x gets cancelled, minus 1. The result is minus 2. Therefore, the option is P. It is the answer for the fourth one.